All right, well, good afternoon. Welcome to the first lunchtime lecture series of the new year. I hope everyone had a nice holiday season. The Interior Museum hosts this lecture series each first Wednesday of each month, highlighting the various workings of the Department of the Interior. And we're very happy to be highlighting USGS in multiple water-related programs this winter. So please check back with us and please keep coming back to the lecture series. We love seeing familiar as well as new faces in the audience. Our evaluations are at the side today. Usually they're on the seats, so if you're looking for one of those, we appreciate your feedback, and any ideas for future lectures are always appreciated as well. I'm pleased to be presenting Bill Cunningham. He's the Senior Science Advisor for Groundwater at the U.S. Geological Survey in Reston, Virginia, and the Chief of the USGS Office of Groundwater. His office provides leadership in the development of techniques for the collection, analysis, and interpretation of groundwater data and information across the United States. Bill also serves as the co-chair of the Federal Advisory Committee on Water Information Subcommittee on Groundwater, where he's responsible for the development and management of a nationwide groundwater monitoring network. He's a recipient of the Department of the Interior Meritorious Service Award and is a fellow of the Geological Society of America. Please join me in welcoming Bill Cunningham.
Wow, applause. I can't believe it. Thanks everybody for coming on this last week of the Leave User Lose year. So I appreciate that very much, to see some smiling faces out there. I'm very passionate about groundwater, and so we're going to learn about groundwater today. I tried to spice up the title and the description of this a little bit with unlocking the mystery of an unseen resource, because we don't see groundwater, and consequently it is often, like many things we don't see, misunderstood or even ignored. And we'll go and I guess before we get started, this first picture here, you can say that you saw groundwater, because that is the Snake River Canyon. That's the Snake River Plain Aquifer flowing out of the canyon wall into the Snake River. And so an example, one of the few, of where we see groundwater. So this outline describes what I'll be talking about today: a brief history about groundwater science at the USGS. And we have a long history, but it will be brief here. Understanding groundwater, so basic concepts about groundwater, a little bit about groundwater use in the U.S., and then some groundwater stories with those concepts woven into it. So we'll talk about groundwater surface water interaction, about groundwater depletion, about pumping-induced land subsidence, groundwater and stream quality, why groundwater matters when it comes to stream quality, and groundwater and ecosystems. Groundwater is also important in many instances with our ecosystems. And I may go by hand here. Here we go. So, groundwater science at the U.S. Geological Survey. So the U.S. Geological Survey is more than 100 years old, 1879, I think. And from nearly the beginning, groundwater has been a part of the USGS. So this document on the left here is a nice report that was done in the 1980s describing 200 years of hydrogeology, which is the study of groundwater in the United States. Of those 200 years, really the USGS was the primary science agency and the primary science, putting the science forward for groundwater science in the U.S. and in the world, frankly. So the picture on the top there is G.K. Gilbert, who in 1896 published a report, a USGS report, on groundwater that described groundwater in the Arkansas River Valley. So very early publications coming out of the USGS were about groundwater. In the lower left there, there's a photo of Darton, who in 1901 produced an excellent report at the time covering about 5,000, I believe, 5,000 square miles. Does that sound right? On horseback and carriage, to describe the Dakota sandstone, which is a very productive aquifer, the Dakota Aquifer, in that part of the world. And in 1905, really a series of 4 groundbreaking water supply papers were produced by Mendenhall in Southern California. And those reports, actually Mendenhall ended up being one of the directors of the USGS. At the time, he was chief of the groundwater branch. But Mendenhall produced these 4 reports, and actually that work in Southern California, in the LA Basin in particular, convinced the city managers that the groundwater supply that they were counting on at that time in the LA Basin was not going to be adequate for the growth that they expected in the future, and convinced them to look elsewhere and that was sage advice, as it turns out. From 1912 to 1946, O.E. Melnzer was the chief of the Division of Groundwater at the USGS, the geologist in charge of that group. He is the father of hydrogeology, not the father of the hydrogeology in USGS or in the US, but the father of hydrogeology. The science of hydrogeology really evolved out of work done by him and the scientist in his charge at that time. Quantitative methods in hydrogeology, or transient, as changing through time hydrogeology, was really born with a hydrogeologist and engineer with the USGS, C.V. Tice. C.V. Tice worked primarily in New Mexico and published 2 landmark papers in the 1930s and in 1935 and 1940 that I've listed here on this slide. And in fact, those of us who study hydrogeology or civil engineering learn still today the Tice equation that he published in 1935 to describe the relation between lowering the water table, the piezometric surface, and how that is tied to the aquifer around it, and also the discharge out of that well, and how that changes through time. And so, in 1940, his source of water derived from wells was really a groundbreaking work to show how the water balance works as you pull water out of the system, what that impact is. And basically, he said that if you take water out of the system, in order to do that, you either have to increase the water that goes into the system, or you remove it from storage, or you decrease the amount that leaves. Sounds very simple, but in fact, we often forget that still today when we look at groundwater systems. So I'm skipping a lot of time here, but chronologic time. But the groundwater tradition in the USGS continues today. There were many major advances since C.V. Tice to today. I don't have time to go into them all, but I did want to mention that even today, the USGS is an international leader when it comes to groundwater studies. And an example I show here is a computer code called ModFlow. And we'll look at some slides later that use this tool for computer modeling. This is an international standard for simulating and predicting groundwater conditions and the interaction between groundwater and surface water. Just recently, within the last year, there was Armenia had a problem with groundwater depletion. They talked to our USAID about that problem and said, we're having this problem. We want to use ModFlow and call the USGS to help us. So those things happen more than one might expect. So let's transition to some of the basic concepts about groundwater now. This is a water cycle diagram that your children see in school and that we all learned at the time. And so groundwater, what I want to mention here is just that groundwater is a piece of the water cycle. It is a dynamic piece of the water cycle. Slow moving compared to surface water runoff, compared to precipitation, but it is a dynamic piece of, sorry, my laser pointer is, it looks like it's out of juice, or, you know what? I turned it off, so, and you can't see it on the screen, so I will use, I'll use the mouse to do that, which is probably better for the recording as well. Groundwater is an important piece of that water cycle, and we'll talk more about that as we move forward. Here's another diagram in the upper left of the water cycle. This time it's quantified. So if we look at, so these are numbers associated with those different pieces of the water cycle. Here we have in cubic miles for the Earth. So 27,000 cubic miles of precipitation fall on an annual basis. Looking at it in that way, groundwater and groundwater storage is a significant piece of that 2 million cubic miles per year. So to put that in perspective, when it comes to fresh water, we look at this lower right-hand corner. And so of that total water, global water amount there, as we've all learned before, most of it is in the oceans. The largest piece of that water is in the ocean. So when we're most interested in fresh water for consumption and irrigation, fresh water is only 2.5% of that global water pool. Of that, so, and then if you look at that chart to that bar to the right, that is that 2.5% and how it is distributed. Of that, 69% is tied up in glaciers and ice caps. So that's out of our. And you want to say that number is shrinking over time? Is that what you're thinking? Okay. And so of that, groundwater is 30%. Surface water is only about 1% of that. So groundwater is really the largest reserve of fresh water that we have accessible. How does that groundwater occur? So there are a few things in this diagram. Bear with me as we go through some of these concepts. The first I want to indicate are these bottom three diagrams that show how groundwater occurs in the aquifer. So there are three different types that are shown here in these block diagrams. The first is indicating grains of sand or other of clay or other subsurface materials that that make up the earth. The water in that is present between those grains and finds its way flowing between those grains in the groundwater flow system. That's one of the primary ways groundwater occurs. If you look on the far right, it's another way that groundwater occurs is in solid bedrock and it occurs in the fractures in solid bedrock. All bedrock has some fractures in it. Groundwater occurs in those fractures. It is rare that we have the middle case, and this is called karst or caves beneath the ground. So the only case where we have, quote, underground rivers is in that case of karst. And so those are rare, but can be very productive. So when you hear from someone that their well in Massachusetts comes from an underground stream in Canada that is flowing down and giving them great water, that's incorrect. Okay, there are long flow systems, but not in underground rivers providing that. So that's part one. Part two is that this diagram here, you'll notice these flow lines on here. So groundwater occurs from, we have precipitation coming down through this recharge area. It seeps through this brown area here, the unsaturated zone, and into this unconfined aquifer. That is the groundwater, and this is the water table defining the top of that. These flow lines are labeled with relative time. It's a very important concept, a critical concept for understanding groundwater, and that is that the travel times for groundwater can be days, years, centuries, or even millennia. So in understanding systems, and we'll talk about this as we go through the hour today, it's very important to understand that time is a big factor, and that some groundwater flow systems are very quick and relatively shallow, but even through, you'll notice there are flow lines that pass through this, what's called a confining bed. And so that may be a finer grain, a clay, for instance. Water passes through less easily than a sand. Water still passes through. It just takes much longer, and that has an impact on how the system works. The diagram on the right is kind of a cutaway from what would be beneath a homeowner's well. And this is an example of the far right-hand block where we have the soil zone here, the water table, this blue line, and the well completed in this fractured rock. So the water that's coming into that well is coming just from these fractures, not from the solid piece of this rock, but from the fractures. So it's critical when you drill a well that you intersect those fractures to have flow to the well. Okay, now a little bit about groundwater use and the importance of groundwater. About half of the nation drinks groundwater. Nearly 100% of our domestic supplies, rural domestic supplies, rely on groundwater. The rest are generally on springs. That is not classified as groundwater with this. A little over a third of public supplies come from groundwater. That's actually in it's not a third in every state, but every state has some piece of the population that groundwater is supplying the public supply. 43% of irrigation comes from groundwater. And two bullets there at the bottom, groundwater also sustains flow of streams and rivers and maintains aquatic ecosystems, and we'll talk more about that later. So here's a diagram. The USGS does a water use compilation every 5 years. That compilation is done by in gathering information from state agencies that compile for their state water use into different categories. That information is provided to the USGS. The USGS does a compilation every 5 years. The most recent compilation that's been published is from 2010. The next series of slides will summarize those results from the perspective of groundwater. So this slide first shows the relative distribution across the country of groundwater use. So this is total pumping, and as you can see just by the shading of this, the amounts aren't that critical, but just by the shading that Florida, Arkansas, Mississippi, Texas, California are big groundwater users. And if you notice, it's slightly, the western part of the country is a little bit darker on this, shaded on this, meaning that there's a little bit more pumped in the western part of the country. When you look at just public supply, here's the distribution. Again, Florida, Texas, and California stick out here in water that's withdrawn for public supply. But as I mentioned previously, it is used throughout the country. How about for irrigation? Again, irrigation is groundwater is used for irrigation throughout the country, and there is a little bit more, in fact, here in the western part of the U.S. So, and this diagram provides a little more information about that irrigation groundwater use. So on the left-hand side, here we have the withdrawals for irrigation in million gallons per day, and two different bars, one for the 17 western states, one for eastern states. There's 48 states here in this compilation. So this diagram shows, I think, two things to point out. One, the significant amount of irrigation, of groundwater pumped for irrigation in the western 17 states, but also a trend that is interesting. If you look in the eastern states, that trend for irrigation groundwater use is increasing. What about by aquifer? And so the USGS here in the lower right-hand corner has produced a principal aquifer map. So 67 principal aquifers across the country, and based on work that has been done over the past 20 or 25 years. And this map then can be used to take a look at groundwater use within those principal aquifers. And so this bar chart here shows by the way, about 30 of these principal aquifers across the country produce 95 to 98% of the groundwater use in the nation. So most of it comes from about 30 principal aquifers. But by far, the most comes from this aquifer in the center of the country, which we call the High Plains, also known as the Ogallala. The Central Valley Aquifer System in California is next. The Mississippi Valley Alluvium in here is next, and basin and range aquifers in basin fill aquifers here in the west. And the Floridan are the top 5, and the Floridan is this blue unit here, are the top 5 producing aquifers, principal aquifers across the country. So overall water use, what are the trends? So when this came out last year, now in 2014, a little more than last year now, since we're in 2016, it was interesting. It made some news that water use, overall water use in 2010 went down significantly for the U.S. Compared to 2005, and that's a trend actually. The decline is new, but it hadn't been going up nearly as much. So a large reason for that are improvements in use of water by thermoelectric plants, which is a piece of the water use compilation. But if you'll notice, there is also right here, this bar is groundwater. There's a slight decrease over the past few 5-year compilations in groundwater use as well. So as a nation, we're actually using less water now than we did 5 years ago. Okay, so let's transition now into the groundwater and surface water interactions. How do groundwater and surface water interact, if at all? And so there are 4 diagrams on this slide indicating a gaining stream and a losing stream, and then different disconnected streams. And as we go through the day here, we'll see where these are important concepts in understanding some of the kind of case studies that I'll show here. In a gaining stream, this water table that we looked at earlier is discharging to the stream. And so that's a common situation, a gaining stream. It's gaining flow from the groundwater system. Some streams also lose, so this stream is actually feeding the groundwater system. We have some situations where that water table has moved away from this, no longer connected to the stream, and that causes some problems as far as, well, calculations wise for a groundwater person, as far as how the flow gets down through that saturated zone if there is flow in the stream, and in this example there is not. So we have all these types of streams, and in fact it's dynamic in that a given stream in certain situations can be gaining and in the same location in a different recharge, different precipitation, may be a losing stream. Well, so across the country, what are the groundwater contributions to stream flow? And using a technique called base flow separation, where you can look at a stream flow hydrograph, or the stage of a stream through time, you can determine how much of that comes from groundwater. And through these studies, 54 streams were analyzed across the country in different geologies, different physiographies, and different climates. This diagram shows the results of that analysis of 54 streams, and the range of this is the amount of groundwater that is flowing into that stream in the gaining stream example from the previous slide, how much of that is contributing. And we'll just take a look at this, at B here and C as an examples of the extremes. Here in B in North Dakota, this is an aquifer of silt and clay, fairly fine grained, not a lot of groundwater movement through it or slow movement through it. The stream flow is made up of 90% runoff, only 10% groundwater. In northern the lower peninsula of Michigan in the north, there is the Sturgeon River example. The Sturgeon River, 90% of the flow is coming from groundwater. Only 10% of the flow in that river is from precipitation runoff to the stream. So it's important to understand in a system that you're studying whether you're in a 90% or a 10% or somewhere in between. And in fact, half of the water in the nation's streams comes from groundwater. So here's an example of a quick example of how connected or not connected these streams are. So this is the Santa Cruz River, south of Tucson. This blue line is the Santa Cruz River flowing through in 1942. That you can't see it because of the riparian vegetation, or the trees that are growing up to the up against the stream. If we look at that same diagram or same photo, we're in the same position. Here's the same rock. This is what the Santa Cruz River looks like in 1989. Groundwater pumping has disconnected the stream that was gaining from the groundwater system. It no longer flows except in extreme events.
That's dry.
And so, I'm sorry?
That's dry.
That is dry. In this image, it is dry. That's right. Yep. So that's an example of pumping effects on stream flow. This a report that I brought a few of them on and Diana put them on the table over there. That you're welcome to grab those. I don't want to take them back with me, but there's a diagram in there that I've reproduced here, and it shows 4 different situations, or the same situation over time for pumping, that shows pumping effects on stream flow. So in A here at the top, we have the situation we've seen before. We have recharge coming in, flowing through the groundwater system, discharging to the stream. In B, we have installed a well. That well is pumping, and these arrows show where that water is coming from, that groundwater is coming from. So the well is producing water, and in early time, that water comes, we describe this as coming from storage. So it's coming from aquifer storage right in the vicinity of that well. As time progresses, and you'll notice there's still water discharging to the stream, even though that well is here in this diagram. In longer time, at the same pumping rate, less water is coming out of storage here. Some of these arrows are being intercepted. Some of these arrows are now moving from the stream toward the well, and there's still a few arrows discharging to the stream. In the bottom, after longer time, water is actually, if the pumping is high enough, water is actually traveling from the stream into the groundwater system to that well. And these concepts, one where water that would have flowed to the stream is intercepted by the well, and another where water is induced from the stream into the well. Those two together are streamflow depletion. And so this diagram shows what I just described, where in early time, that water is coming from storage. That's what this line shows. We look at pumping time. So over time, the amount of water coming from groundwater storage approaches zero. While it does, the amount of water coming from streamflow depletion, those two concepts added together, approaches 100%. The problem with it, so we understand this, the problem with it is dependent upon pumping rate, it is dependent upon the aquifer, it is dependent upon lots of different factors, the geology of the system, which controls the aquifer and how the system flows through it, how many wells are pumping. All of these things complicate this diagram, and a lot of our work is to understand and predict what these impacts are going to be. Weather is a variable too, as well. How much recharge or precipitation comes into the groundwater system. It's a key variable in it. How much evapotranspiration is happening, if you have trees pulling water out of the system or not allowing water to get into the system. Well, all of those things complicate that analysis. One of the things that if you understand this, you will be head and shoulders above your peers when it comes to understanding groundwater. This diagram right here, that's the reason for coming today, right? Is that even after that well turns off, the streamflow depletion still continues. The amount of time that continues is complicated, but we know it does continue. And here's why. If you look at that same diagram where we've lowered the water table into what we call a cone of depression around the well, there is a volume of water that represents. As the water is flowing through, as soon as that well turns off, before anything else happens, it has to fill that cone. So even though you have turned off a well, if you have a well, you know it's impacting the stream, even though you turn off that well, the groundwater still has to fill that cone before it can then travel on to that stream in this diagram. That's what this is trying to show. And so if we have a situation which happens quite frequently, we know there is a complaint that the well X is impacting stream flow and affecting this particular organism, and we have to turn off the well and solve this problem. It's not instantaneous. That turning off that well will change that. It helps, but it's not instantaneous. And the amount of time that takes, there's that word again, time, that it takes is amazing, actually. And so this next diagram shows an example of that. This is a river in Arizona, and Stan Leak and Paul Harbaugh and Stan Leek have reproduced this here. Stan Leek created a groundwater model of the sea aquifer in Arizona that contributes flow to this stream. In this model, and this is one of the reasons we do models, is to be able to make predictions like this. So there are two scenarios in this model, just A and B. Scenario B, there's a little higher pumping rate than scenario A. Those two pumping rates turn off after 50 years of pumping. And so this is cumulative streamflow depletion here. So it's always increasing because you just add a little bit more to it every year. So there's a positive slope on that. Once that levels off, there is no more depletion because of the way that this is being calculated. After 50 years, pumping stops. In this model, it takes until, would you agree, it's about here where it starts to level off? And that is at about 95 years. So it takes an additional 45 years before streamflow depletion stops in this example. And the reason for that in this particular example is that the wells were located very far from the stream, and the pumping rates were not that high, and so it takes quite a while for that impact to be seen. Yes?
So it takes almost the same amount of time that you had pumping to actually have it to a point where it was pre-pump?
I would say in this example, yes, it did, but I could not make a blanket statement about that.
Have you seen similar reactions to other areas, not necessarily double the time, but...
Yeah, it's a good question. I don't really know, Camille. Yeah, I'll check and see. Yeah, yep. Because it's dependent upon. Well, these capture maps talk a little bit about that. So it's a complicated concept, and so one of the ways that Stan likes to illustrate that is through these capture maps. And so we use a groundwater flow model, ModFlow in this case, to illustrate that. And this is throughout that modeled area that is shown here, and this is the San Pedro River Basin, southern Arizona. And so a well is placed in every cell. There's a grid in a numerical groundwater model, and in every cell of that grid, one well is placed and the model is run. And then another one is placed and the model is run. And you do that for every cell in the grid and look at, okay, what is the impact on, in this case, streamflow depletion? And so here's an example where looking at layer 4 of the model, so that's just describing kind of how the computer model is set up, and the fourth layer in the geology happens to be, in the hydrogeology happens to be where the well was placed. So in that fourth layer, after 10 years, on the San Pedro River here, and this is Mexico and this is Arizona, this part of the river here we're looking at about 80% is a fraction of pumping that is captured. You can see different places are affected in different ways based on the underlying hydrogeology in this case. And if you're putting a well in up in this area, it's farther away. There's much less effect on the stream, but it's not uniform because it is a function of recharge rate, geology, and other factors. After 50 years, this is what that same diagram looks like, installing a well and what that impact might be on capture of the San Pedro River. So these diagrams are very helpful to show what the impact will be over time, the fact that it does take time for these things to happen, and if you are going to develop the area, where you might choose to develop it with the least impact. Another thing you can do with these is scenarios such as one of the things that Arizona does, California does, and many other places across the country are doing this now. It's a concept called artificial recharge, and it's where you put water into the groundwater system, often by spreading it in spreading basins, sometimes by injecting it, but in this case, you can run those same scenarios by applying that artificial recharge to the groundwater system and seeing where you get the biggest impact in a positive way, I would assume, is what you're looking for here on Streamflow. And so,
where do you get the water from?
that's a great question. Well, in the case of Arizona, they have. Well, I don't know that they have it in the San Pedro, but there are places where there is excess water from surface water that they may spread. In the case of when water is injected there into the ground, that's aquifer storage and recovery, that's called. It could be an example like Hilton Head Island, for instance, on the East Coast, where it has a transient population, high in the summer, lower in the winter. They have a water plant that makes X amount of millions of gallons per day, some from groundwater, some from surface water. They continue that all year round. During the winter, then, they have excess water, and they take that excess water, pump it into the ground.
Groundwater?
No, treated water that they pump into the ground. And then they pull it back out in the summer when the summer population increases.
Underground reservoir?
Like an underground reservoir that doesn't have the problem of evaporation, for instance. There are other problems, but that's not one of them. Other issues, that's not one of them.
Question on that.
Yeah.
We're hearing a lot about Oklahoma now with the pumping, injecting water into the basin there, a lot of earthquake issues. Do you have the same problem here when you start doing that?
No, is the short answer. I'm not an earthquake expert, but the stresses involved, etc., are just completely different, and the pressures involved are completely different. Which, these are the recharge basins are gravity fed. The injection into the aquifers are at much shallower depths too. So. Yeah, well, I'm going to keep going here. So I want to talk a little bit about groundwater depletion. There are a couple ways to look at groundwater depletion. This is a map of water level change that have been more than 40 feet since pre-development conditions. As you can see, there are areas all across this country where water levels have declined that much. But there's another way to look at that, and that is volumetrically. And so a couple of years ago, Lenny Konikow at the USGS wrote a report compiling groundwater depletion volumes across the country, based in part on those principal aquifers that we looked at earlier, 40 major aquifer systems. And the highlights of that report are shown here. The total depletion since 1900 has been about 1,000 cubic kilometers. That's about twice the volume of Lake Erie. That's about 811 million acre feet for those of you who think in Western units. The largest volumes come from the high plains, here the Mississippi embayment and the Central Valley aquifers. And if you look at this graph in the lower right, this is the total depletion for the nation. And from 2000, again, it's cumulative, so it's increasing here. And you can see from 2000 to 2008, 25% of that depletion actually happened, which there is a measurable contribution to sea level rise here. Not a huge contribution, but a measurable contribution. So that is another way to look at groundwater depletion. We talked about how pumping can affect stream flow, and so this is that Mississippi embayment aquifer here, and let's look at just before 1980 when this depletion started, according to Lenny's analysis. So we've plotted the stream flow, discharge in cubic feet per second, at the Sunflower River in Mississippi, which overlies this aquifer. And when that cumulative depletion began, this is what the minimum annual stream flow from that Sunflower River did. So instead of being in the 100 cubic feet per second range, now it is in the 20 cubic feet per second range as far as the minimum annual stream flow. I'll skip that and say just because it's not everywhere where water levels are decreasing. There are actually areas in the country here where that depletion is improving. Water levels are improving, so this number is positive or is negative. In these blue areas, in Arizona, southern Arizona, here in the coastal plain, in this area around Houston, Texas, water levels are actually increasing because of management actions that have been taken. And here's an example in North Dakota, currently, where these hydrographs show this is groundwater level over time, that water levels were declining through about 1994, but have significantly increased since then in North Dakota. That overpumping, however, can affect land subsidence in certain situations. And so not only does lowering the water level increase the pumping cost and can affect water quality and can affect streams and lakes, but land subsidence can be an issue, in particular in the Southwest. And so these are areas in California where land subsidence has been detected from groundwater pumping. This is a famous photo here on the left of Joe Poland, a major groundwater scientist in the USGS. This picture's from 1977 in the Central Valley of California, showing 9 meters, so nearly 30 feet of land subsidence that has occurred from 1925 to 1977. So the whole piece of the valley declined because groundwater has been pulled out of it. Now, it doesn't happen everywhere. It happens in certain situations, and here is why. If you remember those blocks with the water in them, that block, if that block is clay, those particles are actually supported those clay particles are supported by the groundwater. The skeleton of the aquifer, of the rock, is supported by that clay. When you pump water out and the water leaves from that clay, that water is no longer there. Water's pretty incompressible, and it's no longer there, and so that structure is lost, and that clay compresses. When that clay compresses, you see the effect at land surface. One of the problems with that is that once that compression happens, most of it you can't get back. There is actually subsidence that happens, it's called elastic subsidence, that happens all the time. You pump water out, the land sinks a little bit, water comes back in, the land rises a little bit. We're now to the point where we can measure that. We measure that from space, that movement up and down of the aquifer. It's relatively small, nowhere near 30 feet. But that's how this works. So that was historic subsidence. Unfortunately, in the Central Valley of California, particularly now, with the need for water in the Central Valley, and groundwater is often where people look under drought conditions. This is Michelle Sneed from our California Water Science Center in 2 locations in the Central Valley where additional subsidence has been shown. And you might think, well, that it's if you've been to the Central Valley, it's flat. You can't really tell anything's going on. However, if you look at this diagram, these areas are areas of subsidence that has been detected at various ranges of that subsidence. These dashed lines are canals. And if you have differential subsidence with that overlying infrastructure, a canal, a road, a bridge, particularly a canal, you may have water start flowing a different direction. Okay, so this is something that we're keeping a very close eye on in the Central Valley of California. And that can be done. It's done in various ways. It's done on the ground, but it's also done. It is also done from space using radar signals, measuring the distance from a satellite to the ground, and then measuring that over time. It's called interferometric synthetic aperture radar, or INSAR, where we measure that. And this image is from the Central Valley of California, and how we can monitor that subsidence and then also check it on the ground as well. Two other examples here. One is groundwater effects on stream quality. Here we're all concerned about the Chesapeake Bay. We hear a lot in the news about what's going on with water quality in the Chesapeake Bay. So what you've learned about groundwater so far today, and how it interacts with surface water, and the time associated with some of those flow paths, how long do you think it will take to see the effects of nitrogen-reducing best management practices implemented at the land surface to reach Chesapeake Bay by groundwater transport to streams? I hope with what you've learned today, you say that that's not instantaneous, that when something happens at the land surface, based on those flow paths, it might take some time for you to see that. We don't yet know how much time, but it might take some time. Well, so the study that Ward Sanford and Jason Pope released in 2013 did that. They looked at a groundwater model in the Delmarva Peninsula. They did a nitrogen model as well. Combined those two to show what the difference would be. So in the Chesapeake Bay watershed, in the coastal plain province, the lag time is what they describe it. That's the time of travel for that particle of water in one place to move through the groundwater system and discharge to a tributary to the Chesapeake Bay. More than half of those particles, it's more than 13 years. For a good chunk of it here, more than a quarter, it's greater than 50 years. So if you implement a change, best management practice change, at land surface, the impacts of that change, the groundwater portion of that change, may take 50 years or more to be seen as that nitrogen is discharging to the system. And so that's a critical piece of information that needs to be understood as we generate these management actions. And in fact, we need to know that impacts of those changes may not be seen right away. This diagram shows the total load of nitrogen into the Chesapeake Bay. This is the goal of the total maximum daily load here. And these colored lines show at different reductions how you can get to that, what US EPA and the states have tried, their goal of trying to get here. Even when if we don't increase the amount of nitrogen that is distributed over the land surface, we will still see a slight increase in loading from the groundwater system. And the reason for that is that the water that's flowing into the system now, some of it's greater than 50 years old. It's not contaminated by nitrate. There's still clean water in that portion of it. Because fertilizers have been used since about the 1960s. So when that relatively clean water no longer is flowing, it's actually going to go up for a little while, even if we don't increase the current usage. And so that's a fact that we need to understand as we measure the water quality in the surface water system. Last example here is groundwater effects on ecosystems. And so this is an example in the Delaware River, where the dwarf wedge mussel is particularly sensitive to temperature changes in the surface water system. That's a sensitive area. Dam operations depend or can be affected by this endangered species. And we know that these organisms like these cooler areas in the surface water system, but we don't know the details about that. And so in order to do that, this system was created where a reconnaissance using a thermal camera was done, and that shows this example here. And this is warmer water here. This blue water here is cooler water coming into the system, and that's surface water. And the groundwater system was investigated using this rod with fiber optic cable wrapped around it like your telecom wire, and temperature is measured in that fiber optic cable. The results of this indicate that this is a cross-section through that stream. We're looking at the groundwater system flowing here. This is the bottom of the stream. These are the little critters here, liking that cooler groundwater flowing in. And so what this study showed was that this groundwater discharge is a critical habitat for the dwarf wedgemussel. The ultimate refugia for the wedgemussel is actually a combination of hydraulic protection, in other words, having enough flow through the stream, but also making sure that we continue to have those cold water inflows into the stream to support that ecosystem. So this FLIR camera is pretty cool. I'm going to end with a little video here showing you how this camera works. This is an image of a surface water body here. As I play the video, we'll zoom in here. So this is the color, and sorry, there we go. This is the color infrared. We're going to see here a few examples to look at. The blue water is groundwater flowing into the surface water system. The red it's all surface water now. You can see you're looking at groundwater here from a groundwater seep, a pipe in the system flowing into the groundwater. And if you look, there's a really cool thing right here. You can actually see, if you look right here, see that little blip? That's actually a gas bubble coming up through the water and exploding at the surface. So this is what groundwater looks like merging into surface water at the skin of the stream. Okay, take-home messages. Groundwater happens in pores and fractures, not in a lake or a stream underneath the ground. Groundwater and surface water are connected. Time in geology is critical. Aquatic organisms depend on groundwater, and understanding the system is critical to making decisions about water, surface water, or groundwater use. Thanks very much. So I'll stick around if anybody has any questions, but feel free to run off.
That's great.
See ya. Yeah.
So I'm a nuclear engineer
Mm-hmm.
at Lowell, so we have a lot of civil engineers that understand what you're talking about. But I'm just trying to get enlightened because, fracking is a big deal. I think it was alluded to, but not really mentioned.
Right. No, I didn't really
Yeah,
mention
the whole water use is huge. It connects to energy somehow. It all connects.
Yep.
In fact, water is more critical, or as critical as that of electricity in the world in general, not
I
just
would
the
agree.
US.
Yeah.
So it's all, and global warming.